Okay, see, we are going to continue our discussion on derived responses and dynamic effects as we had in our last class. As it was mentioned, the basic six modes of motion, the rigid body motions, are very important, but from practical point of view, some of the effects that result from those six modes of motions become even more important, which we call derived responses, like we were telling about things like deck wetness, and say green water shipping. We have mentioned all this, I will just for sake of continuation I am mentioning. Then we have got forefoot emergence and slamming. Then we had motion sickness, for example. Then we have added resistance, etc. Say propeller emergence, etc. Okay. See, so we were talking about this. So we will continue talking maybe some of these aspects little more again, because what we would like to talk today is not only how we can estimate them, also how practically important information can be derived for these quantities in irregular sea. For example, slamming, you would like to know for a design in a given sea state how many times it slams per hour, how many times water comes on board the deck per hour, etc., etc. These are the quantities that may be of more relevance than directly computing just the number. Now let us continue this part little bit more to see this deck wetness and forefoot emergence. Now let us just think of this relative motion concept. Now if I had a wave or rather body, let us say this represents the vertical velocity of the body, okay, and I will take another pen, and this represents the wave, maybe smaller. Now what is happening, see here, now let us talk of a point, we will take somewhere here. Now say this line represents, this black line, the motion of the ship. So supposing I take a shape here, bow point, say point B, okay. Now what is happening, see here at this point, this height is my vertical displacement of point B, okay. So let me call it Z at point B, whereas this blue line is eta at that location, that is incident wave height. See, once again, this is my vertical displacement and blue line is my wave profile. And this is my ship at this instant. So this point B, see it has come up to this height, so that is this distance is my ZB, whereas this is my eta. So what is happening is that this distance, this again with the red maybe, this distance is ZB minus eta equal to SB, what we can call relative vertical displacement of point B. Relative means how high it is with respect to the water profile. Now obviously you can make out from here that if this is T, see this is the draft here, this. If SB is more than T, what happened? The 4 foot has come out, the bottom would have come out, isn't it? See, SB is this much and T is this much. So obviously if SB is more than T, my bottom has come out of water. Now exactly the same way in a reverse case we can show here. For example, if I were to take this red line here somewhere, now this is my body point B. Sorry, I am making this. This is the point B. This is my ship here. This is my point B. Now you see it has come down. So that means this is my, the point has come down. This is my ZB. This is my eta. So this is my, you can say ZB minus eta with a negative sign, and this is my freeboard. F. Now obviously when eta minus ZB is more than F, that means the water has come on the deck. So what, so in other words I can say minus SB greater than F So what we are saying therefore is that, see, both these phenomena actually can be found out by the quantity SB, which is given by ZB minus eta. So if this eta at that location, eta at that point of interest, if this more than some value, say some threshold value, then I will say, depending on how you take it, minus or plus, that 4 foot has come out or the deck has gone down essentially. Okay. So essentially what happened, what I need to do therefore, see, I need to prepare a these regular waves. So in irregular wave if I want to study, I must make a spectrum of this, of SB. Okay. That is very simple to do a spectrum, because what we have seen last time, that ZB is nothing but, once again if I were to draw a ship like a ship case, with cross section etc., and if I take a point here, remember that there this Z at point B is Z of the hull minus x of point B into theta of hull, that is pitch. Why? Because remember that my Z is positive here and theta is positive here. Like if you take the cross section, because what we have taken is x here, y here, so downward, nose down is positive, so we find out this. So you see, that means that vertical displacement Z at any location B is equal to heave motion, I will just write Z here at heave motion, minus location of the point x location into theta. Okay. Now this, see, ZB is T, let me put this the full thing here, right, this T, it is going to be equal to Z. See, what is Z? Z is amplitude of heave into e power of minus I omega t, maybe e power of minus I beta, beta of heave Z. Essentially it is a, well, sinusoidal function, real part of that, or if you do not like it, let me put the other way down, let me put it this way, it is basically Z A, say cos of omega t minus beta Z. It is something like that, plus or minus. Okay. of which this is my phase, is my amplitude, and then I have got minus xb, theta is again theta amplitude A into cos of omega t minus beta theta. So, this full thing obviously, of course, I can express this way as some quantity, maybe I will wait for the next level. Now, if I were to took SBT, that is ZBT minus eta, remember minus eta t at x equal to xb, okay, this becomes ZBT, which is what on minus, this is actually A cos k into xb minus omega into t, kx minus omega t taken at x equal to xb. Why I am doing all that? Now, you see, if you add this and this entire SB, go to this next slide, that is I end up getting SBT, if I were to write it as Z A cos omega t minus beta z minus xb theta A cos omega t minus beta theta minus A is amplitude of wave cos k x b minus omega t. Omega can be omega e, of course, in our case. This entire thing is equal to an SB amplitude into cos omega t minus beta s. You can write in this way. It is a sinusoidal function. So, where xb will be known, you will be knowing SBA. I will not write the expression, but it is basically a function of all this ZA, theta A, xb, all this beta z, beta theta will be an expression. So, what I am trying to say, see this SBT, this is relative vertical motion itself is a sinusoidal function with an amplitude SBA. So, therefore, I can very easily determine the spectrum for SBT, because my response here, the word response, see here my spectrum, response spectrum, if you remember response spectrum, that is SR omega is RAO of the response square into S wave of wave. This is my RAO for the response square, that is amplitude of the response divided by A square. In this case, I want to have the response spectrum for this particular quantity, which means I have to have RAO to be SBA divided by A square. That is it, there is nothing to it. So, you see, then my RAO therefore, here RAO for relative vertical motion is nothing but SBA by A. So, the point therefore I am making here is that all derived responses are also responses, and I can always determine the spectrum for those responses simply by taking amplitude of that response divided by A as RAO, that is all. If I were to, for example, find out vertical motion spectrum, then I would take ZBA here, that is I will take this quantity, find out the amplitude of this quantity and take that as a response spectrum. So, this part is straightforward part. So, once I therefore can find out this response spectrum for say in this case, so I end up getting here something like that. Again I end up getting here wave spectrum S omega by omega. I end up getting here my RAO for SB, RAO for SB, whatever that is, then I end up getting spectrum for S of omega of SB versus omega. See, therefore, how did I get that? Remember this, how do I get it? By combining an incident wave. Right. And remember that while combining that here, the phase information was there. Remember when I did that when I did this SBA, this one I had also phases there, very important. So that is why in motion spectrum for say heave, roll, pitch, etc., you don't need phases. But when you want to do derived responses, phases are very important because the phases must be properly added to find out the relative motions. Obviously that is important because you see the bow part, if at the same time it goes down and it pitches, obviously it will go down much more. So the phase is very important. That is why when we calculate RAOs, remember that phase becomes equally important because that is very relevant for derived responses. And derived responses are the one that is more important from the practical point of view, for our practical point that we we would like to know. For example, now that we have done this response, now what we are doing, so this is, let us say, my relative vertical velocity. So it is very simple now. I want to know what is the chance of probability of SB exceeding some value f. This will be given by exponential of minus half f square by m0, when m0 is basically, this is the by theory, because the spectrum is again assumed to be a narrow band Rayleigh spectrum always, and if it is a narrow band Rayleigh spectrum, see this one, you can easily find out what is the chance of certain value exceeding some value, that is probability of SB exceeding some threshold value is always known. This is always given by e power of minus s star square by 2 m0, when m0 is the area under the graph. So this is always known. So that means you always know this part. Not only that you know this part, see here my f dash is basically the threshold value. So what I say is that when if SB exceeds f, then I am going to have deck wetness. So what is the chance of deck wetness then? Like this. Of course I can modify f, I will come to that part in a second, but from there I can find out all other statistical properties also. For example, we will see in a minute how I can find out how many times the deck will get wet in, for example, in one hour, or per second how many times it can go up, all this part, or in 1000 cycles how many cycles you expect the deck to get wet. All these parameters becomes relevant from them. Now before I go to this threshold value, there is one more thing I want to tell you, that as far as the threshold value is concerned for deck wetness, see, two more modifications are taken than freeboard, because what happened when I take a ship, as it goes in calm water itself, what happened, it actually undergoes a kind of a trim and squat, because it changes the value slightly, because as it goes there it will actually have a parallel sinkage and a trim. So that modifies this f to f plus some value, some correction, say r1 let me call. So therefore effective deck free threshold value that you get may get modified. Second thing is that sometime when the ship goes down, then see, for example, in this cross section it goes down, water tries to pile up. This is known as swell up effect. You know that water swells up, like if you just take calm water and push it, water tends to push up on the side. This is called swelling effect. So there is some empirical formula for the swelling. So with all that, this maybe says some R2 maybe for swelling. So I end up getting this as effective f dash. So what I do is that I put here f dash. What I am trying to say, take a ship, it has got a freeboard of say 5 meter. But what would happen is that effectively during motion, what you will get because of this squat and because of the swell up effect, it will be 4 meter perhaps. So therefore we are going to say, if my relative velocity displacement exceeds 4 meter, my deck will get wet. That 5 become 4, that terms can be determined from empirical formulas. This is only a question of relation that is available. Physically that is what happens. Okay, so you end up getting that. Now for example here, from this relation also, we can find out that what is the chance that, see, for example, greatest value n cycles, this is going to become n. Actually, this is the formula is that n can be obtained e power of that f dash square by 2 m0. Rather, this is not important. What is more important is time. See, I will just come to this time part. See, for we can find out typical peak period of this spectrum given by 2 pi square root of m2 by m4 second. M2 and M4 are basically, as you know, area under omega e area under the velocity and acceleration spectrum, or you can say integration of omega e square m2 is that velocity displacement spectrum, and m4 is power of 4. Essentially, this is the area under the velocity. See, here we are talking of relative displacements, relative velocity spectrum, relative acceleration spectrum, d omega e, you can see. And the average number of this thing deck submargins this will be n deck submargins is going to be 3600 of into probability of SB exceeding f dash divided by Tp dash. So, what I am trying to see from this relation, you can find out. So, what is happening? See, this part we have done, this part, this is given by that expression that I just gave you last time, that is this expression. So, what it means is that we are forming a spectrum. So, the procedure becomes very simple. I do a calculation, I have all the 6 modes of motion. Now, I want to do my loop 1, what is deck green water shipping probability. So, I will first of all find out this RAO. I know my freeboard, modified freeboard f dash. So, I first find out this RAO, one particular line I find area under that m0, and in next line I simply come back to those relation, this and this, and therefore I output the number of time the deck will get expected to get submerged per hour is that much. Okay. Similarly, instead of deck submergence, I can say propeller emergence. No, typically, for example, the ship, it is going like that, the propeller is here, and if the water is here, the propeller can also go outside. Same thing I can do. Exactly the same thing I can do for 4-foot emergence, that is that this 4 foot is coming out of water. Same relation, because all that will change is that this f dash value will change, the probability will change. Different condition, SB must be more than this, S must be less, whatever. All of them are, what we are doing is measuring this particular some point. In this case, I will be measuring actually this bottom point, whether it is coming out of water. In the deck emergence, I am trying to find out the top point, whether it is coming below water. Okay. See, all vertically. So, this becomes very straightforward procedure, and this is what exactly we do. So, when we do a calculation, see, in typically a sea keeping calculation threshold, we would be doing first the RAO for the 6 modes of motion, that is the fundamental thing. So, I have this RAO for the 6 modes of motion. Okay. Then I will immediately construct all the derived RAOs that I want, like in this case relative velocity RAO, and then I will find out whatever I want. So, these are very simple. Now, let us talk about this part once more. See this for the slamming part, because slamming part requires maybe a little more kind of other like criteria. Now, say slamming, what here we are doing, hull is like that, water is like that. So, this bottom has come out. Okay. So, we know that what is the chance of this coming out, we know that. We have just found out what is the chance of say bottom coming out. For example, this will also be given by this more than some value say t. This, means if SB is more than T star, some kind of mean draft at this location, then the bottom comes out. I know, but does it cause slamming? The next question. Now slamming, what is slamming? It's very important for us to recognize this phenomena of slamming. See, when this goes up, as it re-enters, okay, it will give a very large impact here. And if you were to measure the forces here, you will find out the force with the pressure here will go like that, and very large, like bang, it's going to make a hit. So this bottom will be undergoing a large pressure because it is entering here, and it depends on the impact load. Okay. Now this impact load will obviously cause a very large vibration on the hull, like you are basically like a hammer just banging it here. Now when will it happen? Nobody knows it exactly, but what we do know is that for it to happen, this bottom might have to come out and re-enter, but re-entering has to be also, well, it has been found out, you define them that if it re-enters beyond a certain threshold velocity. Suppose it, see the impact, so if you take a water, now if something is been dropped, okay, now if you drop from much higher height, you will expect much more impact. Why? Because the entry velocity has something to do with it. See, if you are very slowly entering a wedge from outside to water, you don't expect a very large load, but if you enter it very fast, you expect. So therefore, statistically it is find out that there must be a vertical velocity, relative vertical velocity, that is SB dot T, relative velocity, because water can be going up, you may be coming down. That must be more than some threshold velocity, some velocity, say some V star, we will come back to this V star. People have said, you know, this is a question of definition. People say that, well, we will call slamming to have occurred if this happens as well as if the bow has come out. Okay. See, because otherwise this is subjective. Well, when ship keeps going, it has got different kind of velocities, and you cannot call it as continuously slamming. So there are some prescription, but we do know that the load will be higher provided, or the load depends on the relative vertical velocity of that bottom with respect to water. How fast the bottom is entering, at what rate. So people have prescribed certain threshold value. For example, at one time this was known to be 12 feet per second, but there are empirical formula like this can be written as 0.093 root over of GL meter per second. So some norms are there. So what we will say, that slamming to occur if probability of this is more than this as well as probability of this is more than this. People can say that. Now the same spectral theory will work, because what happened, I can also find out the spectrum for this, right. So therefore I have got now here two spectrum. I will just come to that. So for slamming, therefore I will say that relative vertical exceed a threshold value, that is, you can say probability of SB exceeding some T star and probability of SB dot exceeding some V star. If these two together happens, we might define it that slamming has occurred. Okay, like that one can say. Now you see, this can also be easily found out by the same probability function. For example, this we have seen this is given by e power of minus t star square by 2 m0. Let me put this S here as the relative velocity displacement spectrum. This is displacement spectrum, remember this one. This one of course will be given by e power of minus v star square by 2 m0 dot velocity spectrum, which of course is 2 m2s. See here what is happening. Probability at SB is more than T star is of course given by e power of minus T star square by 2 m0s, and m0 is the area under the relative displacement spectrum. And this is of course probability of SB dot more than V is e power of minus V square by 2 m0 dot S, which is of course area under the relative velocity spectrum. Now how do you find out? Again very simple. If I know SB, see when I went back to SB, remember what has happened to SB? SB happened to be SBA into cos of omega t plus minus some beta. So what is SBT? Simply omega into SBA into cos of this thing. So this is my velocity amplitude. So what I am saying is that there is no point of going further and further. When I add these two up, I will end up getting simply this thing. I will end up getting the probability of, if I want to find out Islamic probability, that is SB more than T star and sorry, I should not put it this way with not comma, and SB that more than V star will be a combined probability. It will be e power of minus T star square by 2 m0s plus e power of minus V star square by 2 m0 dot s. So this I can find out. Once again, once I find out this probability of, so that therefore I say probability of slam is this, the chance of the slamming is this. Then of course I can find out number of slam per hour exactly the same way, 3600 by P slam by TP, or TP is again by that like that period we do by that 2 m2 by m1. So you see what is happening. Then this TP I can find out again by this m2 and m1, but I will just tell you that. What? Okay, yeah. Now that's what I actually, no. What I meant is, this, this. When you multiply, it becomes the quotient gets added. Absolutely right. Yeah. This is what I meant. It becomes this. Like you add this up, the quotients up. Yeah, when you multiply. So basically, let me write it again properly. E power of minus T star square by 2 m0s plus V star. Yeah, absolutely. So like that. So what the point therefore I am trying to say here is that, see, all these things are important, very important, but all these things becomes fairly trivial to estimate as long as you have got all the basic motions right. So fundamental point therefore remains is that get the basic motions right, get all those 6 motions right. Now here it means both amplitude and phases. Then it is very easy and straightforward to construct all those derived responses, especially vertical, like what we said for slamming, etc., etc. Easy and because they are because these derived responses are nothing but combination of this. That is the point I am trying to insist upon you. As far as practicality is concerned, you can always find out open up a book and find out the exact relationship. But the point is that it becomes fairly trivial to obtain that. You see, if I have these 6 modes of RAOs and the phases, I can quickly just by one line find out RAO for a particular motion, say ZB, vertical velocity or relative vertical velocity or whatever I want. From there I can find out whatever I want to know again by just one line. So, you know that the interesting point in therefore C keeping turns out to be that you see what is important practically are quantities like how many times it slams, what is the chance of its deck getting wet, but to get those numbers which is more relevant, the effort needed is very less. It is basically 99% effort to get to the RAO for the basic ship 6 modes of motions. Now, for example, this we have talked about these two things. Now, let us talk about something else also. We will talk about this thing in a minute. See, motion sickness. Again, it turns out that motion sickness is connected to actually rigid body acceleration at some location, vertical acceleration on this quantity. People do not know there are certain criteria. It says that if ZPT is within this to this range and omega is within this to this range, people define that there is some the definition of motion sickness index MSI. I just check this sickness index. This is a function of essentially taken to be as some kind of a ZB dot, not bow here of course, I should say vertical motion. Let me tell this vertical acceleration, this actually acceleration, not maybe this acceleration divided by g and other quantities. You can define it. My point is to say is that it is not uniformly accepted. You see, when you are going to feel sick and when you are going to throw up, it depends on some kind of a criteria. It so happens that ships represent the range of accelerations and range of frequencies where you tend to throw up more. You do not do so in a high frequency train, for example, which is, or in a car. It is a question of actually a human body's response. So, what happened then? Why define that? Look, if my acceleration is within this range and my frequencies are within this range, acceleration and frequency get connected because it's omega square into xi 3 dot, then I will call that people fall sick. So, I will define MSI. Then I can if I define something, then I can easily find out the spectrum for that. Then I can easily find out what is the chance in a given C state that my motion sickness index exceeds so and so. So, you see, application becomes straightforward. For example, if I say that look, if my acceleration is within 0.4 g to 0.5 g or say 0.2 g to 0.3 g, then I am going to say that I am going to fall sick. You can find out what is the probability of acceleration between this limit. So, you can say that the ship would have, and then you can define that to be motion sickness index, that is the number of time that threshold value exists over the total time, say 10% time. So, like that, my point therefore to say is that all these derived responses therefore can be obtained more easily, but there is one, and the spectrum becomes very simple, but there is only one which we will talk in a minute, where the spectrum cannot be constructed the way we have done for all other. See here RAO square we do into etc., etc. So, we are doing all that. What again I am doing that this of response, this I keep on doing at omega square RAO for that response square into S wave of wave. That is what we are doing. So, this square is important, right? This is how we are doing for any response, excepting one case that we will see in a minute, where we cannot really do this square part, and that is what we call added resistance. additional resistance that a ship encounters. We will just talk about it in a minute. I just want to bring this up here. Added resistance part. I will continue on this added resistance tomorrow also, but next class also, but I will just want to tell you today the some kind of like idea regarding this added resistance. What happens, see here, that if you were to have a ship going in calm water, we have an R, calm water, that is your resistance that is coming. But if you were to go in a wave, then I get an R. Now, this R happens to be more than this R, that is this becomes R calm plus R added. I mean basically it is more, and if you take this minus that, what you call is additional resistance. Why does it happen? Now, you see, if I ask you this question, why, what is the physics behind this, what will be the answer? Let me just try to understand from you. We have all done resistance course before. So, we know resistance depends of course on skin friction on this area and also wave making resistance. Now, the question is that there will be a temptation for us to tell, because it goes on the waves, my underwater this part is changing, therefore, I will have additional resistance, but that is not fully correct. Why I tell you that, remember, even when I go on calm water, I actually have a wave formation. See, even when I go on calm water, I have got a wave formation around that, isn't it? Yet, what I have done, if you recall correctly, we do not consider that for our F calculation. Why so is because this wave is up and down, and the net weighted area we think do not change significantly. Okay. Now, if there is a wave like wavy kind of like wetted surface, you say that the wetted surface is more or less same. So, here same thing will happen. So, therefore, it is not because of the fact that my wetted surface is changing. What then, where is the physics for which the resistance increases, and why do we talk this in sea keeping course and not in resistance course? That is the point I was trying to tell. The main reason for that, see, and that we need to understand, see, when the ship is going in waves, what it is doing? It is undergoing heave and pitch and all the motions. Now, you take a calm water and you take a ship and make it move like that. What will it do? It is going to create waves, right? So, if I were to by force impose motions, it is going to create waves. These waves obviously carry energy, just like in wave resistance waves. So, what is happening is that these obviously show up as resistance, additional resistance. See, when a calm water my ship was going, it is making a wave resistance wave, calm water wave. But now, on top of that, my ship is also oscillating, going like that. And if I do that, it is going to cause further waves, because any body in calm water, if you want to oscillate, it will create waves. So, this additional wave also carry energy, and this energy, just like in wave resistance wave, comes or show up, the rate at which the energy is spent show up as additional drag or resistance. What is the origin? The origin of this resistance is purely sea keeping, purely the fact that it is undergoing basically heave and pitch motion or motions. That is why it is taught in, or it is a part of sea keeping, additional resistance, you see, because this resistance originates from the fact that the ship is creating waves because of its wave induced motion in the first place, because it is undergoing some oscillation. So, therefore, this resistance formula that we will find out will be all connected to heave and pitch and other modes of motions. Okay. So, now the question is that this particular thing is normally going to be most significant, which I will come back to that in head wave, but I can tell you one thing, resistance. Now, here there is the question, you know, resistance is proportional to amplitude of wave square. Okay. Here also the resistance that is caused is because the waves it is creating. These waves it is creating would be having certain amplitude. Now, you think of this, I have the, let me, because today I am going to just discuss this. So, I have got a calm water here, let us say calm water here, and it makes a wave of certain amplitude A. This wave resistance wave, we are not, forget it, A star or something, but now I have got a wave of certain amplitude, ship is going. So, now this incident wave amplitude, this is my A, this is my incident wave amplitude, remember. Now, this is causing me to move up and down, this move, the body to move up and down, heave and pitch, which is causing me a certain additional wave. Where is the blue pen? So, let us say this additional wave has an amplitude of A bar. Okay. Now, this A bar obviously is proportional to A, because if the A is more, see my linear, if suppose A was twice, my heave would be twice, my heave is twice, maybe A star will be twice. Okay. So, that means this and these are in proportion, but resistance is in proportion to square of this. So, therefore, it is in proportion to square of this. Now, here is where we differ. In all other responses like vertical acceleration, motion, etc., the response was linear function of A, but here my wave resistance or additional resistance is a quadratic function of A, and therefore, the spectral formula will not apply. So, therefore, what is happening now, I will just want to tell you, because it is actually a square function of A bar, this is basically quadratically depending on the incident wave. If the incident wave was to be twice, you would expect this to be 4 times, okay, because it is quadratically dependent. When a phenomena is quadratically dependent to be A, physically therefore, you can think that it is a non-linear phenomena, it is a second order phenomena, because it is not dependent on A power of 1, but A power of 2. So, this is from hydrodynamic point of view much more complex phenomena, because this is what we call a second order phenomena. Okay. Why I am saying all this is because we are going to tomorrow or next class talk about certain empirical formula. Empirical formula has to come because or based on certain physics connecting heave, pitch, etc., because there is no direct way or closed form way to solve a second order problem. This phenomena is somewhat similar to also the fact that in a wave, if I keep a body, you see here, then if I just leave it, what do you expect? You expect it to drift slightly. You expect to drift, isn't it? Why should it drift? See, the first order response tell me that the surge motion is like that. That means if it goes down 1 meter, it should come back 1 meter. It should be oscillating about 1 point. See, if you leave a body, a ship or a floating body just on the water. Now, according to my first order theory, what has happened? If it went down this much, it comes back this much. It is oscillating. So, it should not be drifting about a mean position. You agree with that? No, it should not drift, but in reality shows that it drifts, because you would have seen that it always drifts, so you put an anchor. Why does it? Because what would happen, in fact, if you see this body, it is not going to go like that, but it is going to go slightly like that. Slight drift will be there, oscillate but drift. This drift force cannot be explained by first order theory, because first order theory tells me my xi1 or surge or sway motion is oscillatory about a mean location, but reality shows it drifts. this drift is obviously occurring because some kind of mean force is acting on the body. So, there is a body here, waves are coming here, there is a net mean force is acting, and this is a second order phenomena. This mean force is, what we call. If it was first order force, it would have been oscillating. That means the force would have looked like, but this force is having a mean value. So, it would look like as if on the mean it oscillates. That means there is a steadily I am pushing. That push is equivalent to our added resistance. The physical hydrodynamic phenomena is that push, which is what we call second order force, equivalent to our this added resistance. So, therefore, my point of saying therefore is that added resistance therefore is a phenomena that is not same as other derived responses. It is a second order phenomena, therefore, it cannot be directly computed or found out as an in a simple motion combination RAO type. Therefore, you must have certain special formulas that would have been derived, which we will be talking eventually. Now, the other thing is that when is it most important for added resistance to occur? Obviously, it is most significant when head waves are coming. Waves are here and ship is going here. In fact, that is the only time that you would expect very large heave and pitch and very large added resistance in a head wave. See, added resistance you expect much larger on a head wave condition. Now, I want to tell you this before I go into this formula. This added resistance has given rise to many important phenomena like when a ship goes from here to here, open ocean, it does not go on a straight line, or even if you take the so called the Earth's curvature, it does not go on the line of minimum distance, typical line that aircraft or somebody might follow. It may follow some line like that, or some line like that, or some line like that. Why? One of the reason is because in that line, see, there can be waves coming in some direction. If it actually went this side, it might actually experience more resistance and slow down and might take longer time. So, therefore, it actually takes a route where your total time taken might be minimum. This is what is called weather routing. Depending on the prevailing weather, it actually takes a route along with which it will have the least resistance. But what is the resistance? It is only for the waves, maybe for winds also if there is a wind field there, but primarily waves, which means added resistance become a significant criteria for selecting which way you should go. So, this is added resistance part, and actually we talk added resistance conversely, because a typical ship would have certain power. Okay. Now, you cannot power up more. What would happen? You are having a full MCR rating. So, you are making 16 knots, but because of waves you would end up making 14 knots. So, we can look at added resistance also as a reduction in speed rather than addition of resistance. Okay. So, we will talk about it next class about certain empirical formula of added resistance and how you determine added resistance in a irregular sea, and we will find out that here in added resistance we are not concerned with 1/3 significant value etc., but with average value, because it is average value of increasing resistance that we are interested more. This we will discuss in next lecture, along with like some idea on sea keeping criteria for design and polar plot and things like that. Thank you.